Hi there. Let's demystify infinite sequences together. An infinite sequence is simply an ordered list of numbers that goes on forever. We write these sequences using curly bracket notation, an. You can think of it as a function that assigns a real number to every natural number. For example, consider the sequence starting with 1, followed by 1/2, 1/4, 1/8, and so on. Each term is half of the previous one. The big takeaway today is that these sequences go on forever. Throughout this series, we'll explore whether these lists settle down to a specific value or wander off without bound. Imagine a sequence as dots on a graph. Here we see the sequence 1 plus 1 over n. As the value of n increases, watch what happens to the dots. If the dots eventually cluster around a single horizontal line as n gets larger, that is convergence. We call that line the limit, L. Think of the limit as a target the sequence is aiming for. It is the destination our points are approaching. To define convergence rigorously, we look at how close our sequence gets to a limit, L. Imagine a tiny distance, epsilon. We draw a band around L. If the sequence converges, every term after a certain point, n, must fall inside this net and stay there forever. Here, for our sequence 1 plus 1 over n, see how the points start outside, but eventually hop into the net and never leave. The formal definition says, for any distance epsilon, we can find an n. That n marks the spot where the net finally traps our sequence. Convergence is just that mathematical guarantee that the sequence is headed home to its limit. Not all sequences behave. When a sequence fails to settle on a single specific number, we say that the sequence diverges. This happens when the numbers simply refuse to get closer to a single limit. Consider the sequence 1, 2, 3, 4, and so on. These values just keep getting larger and larger without bound. It diverges to positive infinity. Other sequences just bounce back and forth. Take the sequence that alternates between 1 and -1. It never picks a favorite spot, so it oscillates, which is another form of divergence. In summary, sequences can grow to positive infinity, shrink to negative infinity, or simply oscillate back and forth. If it doesn't approach one single number, it diverges. Some sequences just keep growing. Consider the sequence 2, 4, 6, 8, and so on. As the index n increases, the value of the sequence doubles each time. These points climb higher and higher. Because they grow without bound, they don't have a finite landing zone, so we call them divergent. Key takeaway: if a sequence grows without bound, it diverges to infinity. Sometimes a sequence refuses to settle on a single value, even if it stays within a specific range. Consider the sequence, -1, 1, -1, 1, and so on. Watch how the sequence terms jump back and forth between -1 and 1. It is bounded because it never grows beyond these values, but it fails to converge. Because the sequence oscillates indefinitely without approaching a single limit, we call this oscillatory divergence. It simply can't decide where to go. Let's look at a shortcut called the monotone convergence theorem. It says that if a sequence is always moving in one direction and it is trapped by a boundary, it is guaranteed to converge to a limit. Imagine an increasing sequence like 1 minus 1 over n. Each step moves it closer to 1, but it never crosses that boundary. Because it is monotone and bounded, the theorem tells us convergence is inevitable. It is a guaranteed win for calculus students. Let's look at the harmonic sequence, 1, 1/2, 1/3, and so on. As n increases, these terms clearly approach 0. Because the terms get arbitrarily close to 0, the sequence converges. This part is straightforward. Here's the trap. While the sequence terms shrink to 0, their sum, the harmonic series, actually grows without bound. It adds up to infinity. Always keep lists and sums separate. A sequence shrinking to 0 doesn't guarantee a finite sum. Geometric sequences follow the form r to the power of n. These sequences are fundamental in mathematics and science. If the absolute value of r is less than 1, the sequence terms shrink towards 0 as n increases. However, if the absolute value of r is greater than 1, the sequence terms grow without bound, leading to divergence. This behavior is incredibly useful in computer science, where algorithms often use these sequences to refine estimates until they converge on a correct answer. The Fibonacci sequence is more than just numbers. When we take the ratio of consecutive terms, we find something amazing. Look at these ratios. As the sequence grows, the fractions oscillate and get closer and closer to 1.618, known as the golden ratio. Let's visualize this on a number line. See how the values tighten around 1.618. This is a perfect example of a discrete process creating a steady, beautiful limit in nature. In 2026, understanding convergence is about speed. Does your sequence crawl, or does it sprint toward the limit? Here, the magenta dots represent a fast sequence, approaching the limit in just a few steps. The black dots show a slow harmonic sequence that takes much longer. In data science, knowing the rate of convergence is vital for efficiency. Fast sequences allow computers to solve complex problems in fewer iterations. Did you know that students who plot sequences using visual tools are 22% more successful? Seeing is believing when it comes to math. When in doubt, plot it. Let us watch as we plot the terms of the sequence a sub n equals 1 plus 1 over n. See how these points cluster toward the value of 1? This visual feedback turns an abstract limit definition into an intuitive reality. Plotting reveals the behavior of a sequence intuitively. It is the best way to develop your mathematical intuition. To master sequences, we categorize them into the big three. First, we have convergent sequences, which settle on a specific value. Second, divergent sequences that grow without bound to infinity. And third, oscillatory sequences, the constant jumpers that never settle down. Convergent sequences like 1 over n shrink their gap as n gets larger, landing softly on a limit. Divergent sequences to infinity represent growth without bound. They simply never stop climbing. Oscillatory sequences are the tricksters. They jump back and forth, never deciding on a single value to call home. The most important lesson here is this: always categorize your sequence before you start solving it. Knowing the type guides the method you should use. Sequences are everywhere. They are the backbone of how computers learn. Instead of knowing the answer immediately, a computer makes an initial guess, then refines it over and over in an iterative sequence. By constantly refining the guess, the sequence converges on the correct solution. It is exactly like finding a password or optimizing a delivery route. Think of password guessing. Every attempt helps the computer narrow down the possibilities. Similarly, in logistics, an iterative sequence tests paths, quickly converging on the most efficient route to save time and fuel. This ability to converge on the right answer is what makes modern technology intelligent and efficient. A common mistake in calculus is confusing sequences and series. Let's clear that up once and for all. A sequence is just a list. It is an ordered collection of numbers. A series, on the other hand, is the sum of those numbers. It is the cumulative total. Here's the trap. The sequence converges to 0, but the series converges to 2. They are completely different animals. Remember, a sequence is a list, while a series is a sum. Don't mix them up. The biggest hurdle in Calculus 2 is moving from simple algebra to conceptual analysis. It is easy to get lost in solving for n, but we need to see the bigger picture. When we look at the tail end of a sequence, we aren't just calculating. We are observing how the terms behave as n approaches infinity. Ask yourself, what does the sequence actually do when n gets really large? Does it settle down? Does it vanish? Stop manipulating symbols just for the sake of it. Instead, look for the underlying behavior of the limit. That is how you master sequences. To practice testing convergence, let's examine the sequence an equals n over n plus 1. Let's look at the first few terms. We have 1/2, 2/3, 3/4, and so on. As n gets huge, we can use algebraic intuition. Dividing the numerator and denominator by n gives us 1 divided by 1 plus 1 over n. As n approaches infinity, 1 over n becomes 0. This leaves us with 1 divided by 1, which equals 1. The sequence converges to 1. Since the terms get closer and closer to 1, we conclude that this sequence converges to 1. If you find yourself stuck with indeterminate forms like infinity over infinity, here is a professional tip. Treat the sequence like a function of x and apply L'Hopital's rule. By taking the derivative of the numerator and the denominator, you turn a difficult sequence limit into a straightforward calculus problem. This strategy makes the hard ones look easy. Always remember to switch back to your sequence variable n after you solve the limit for x. Keep practicing this conversion step. We have reached the end of our journey through infinite sequences. These simple lists of numbers are the true foundation of calculus. Whether a sequence settles down into a limit or runs wild into divergence, understanding its behavior is a core secret of mathematics. By mastering these building blocks, you've unlocked the way math describes the infinite. Keep practicing, and you will see these patterns everywhere. You now have the core tools in your belt: plotting your sequences to build intuition, using the monotone convergence theorem to guarantee limits, and identifying the different types of divergence. Use these strategies on your next problem set, and you will crush it. Mathematics is all about that curiosity, so keep exploring, and I will see you in the next lesson.